Yeah, so we started with Bayesian because that is very closely tied to the probabilistic view of things. But we'll try yet another class of classifiers, which is very common uh, in the case of statistical roots of machine learning, which is basically taking an approach to curve fitting. So curve fitting usually is done by means of something like approximating the data points with a simple line. That is why it's called a linear regression. So linear regression is basically one of the simplest algorithm. It's a very simple idea. The idea is that you model the relationship between dependent variable and one or more independent variables by means of simple linear equations. Simple linear regression when you have just two variables y and x. Multiple linear regression when you have multiple explanatory variables present, x1, x2, x3, x4, etc. And typically what you use this is to model a linear predictor function, right? Basically you try to identify what is the equation of the form y equal to m1 x1 plus m2 x2 x3. And unknown model parameters are estimated from the data which you are given. Ultimate goal is basically to come up with, as we did in the Bayesian classifier, something which will give you a model which is the representation of the straight line. When you get a new data point, you should be able to predict the y value given the input values. Just like in the Bayesian case, what we did, we gave a new instance of all the input variables and said which class it falls in. Here it's more regression because it may also be used for putting into classes, but it doesn't make a difference. But idea is typically regression is used for continuous functions. It usually generates an equation which you save for combining to get output function for a specific set of the input variables. So once a predictive model is fit, it helps to predict the future value for a future set of independent variables which are known to be features or variables which help you in determining what is the set of independent variables which are going to govern your dependent variable. And terminology is simple. All the ones on the left hand side are called regressors and the y is called regression. So symbolically, if you see, if you take a single independent variable, it is y equal to mx plus c or beta x plus lambda. If you have multiple dimensions going beyond, say, single independent variable, you get something like this, where you say that sigma of beta xi plus lambda. So, what is the effectiveness of the predictor you have determined? Definitely, when you're drawing a straight line, you will not have 100% of the variables all on the same line. That's never expected. But how do you choose the coefficients of the line? What is the line we choose to model it? That's where you typically create what is known as a distance coefficient. Just like, okay, so what we are talking about is we will ultimately not be able to fit a exact what we call as the every point to be explained by a model. But typically when you do a model like we saw in the Bayesian case, we try to create a probability, right? In case of here, instead of probability, we are creating a model where we are fitting a straight line to accommodate maximum explanation of the data set. So how do you measure how well a particular model is being explained? That is where we have this notion of root mean square error, or error which is determined by how well is this, or how distant, or what is the distance between each point and the predicted model. So that is where we have this notion of least square minimum distance error between each of the points. While there are one way is to calculate it based on the distance, but if you see here, there are several approaches to calculating the errors. We can just do a mean absolute error, which is the basically distance between absolute distance between the points, and then you try to sum up and get an average. So what we do is but normally we don't want to use absolute error because of its bias with respect to the sample. Instead, what you do is you try to capture the sum of squares of that distance, and we try to create an average of that, and then you take the square root. Or you can do relative absolute error, which is saying that whatever was the uh, net distance sum from the individual points, and you divide by the distance from the average, sum of the distance from the average. Similarly, you can have root relative mean square error. But important thing, just like what we had in case of unsupervised learning, different distance measures, right? We had measures like the what is that, Euclidean distance, which was basically measuring absolute distance between 2 points. Or in case of Manhattan distance, we were measuring individual features, absolute difference in the values, and then summing it up. Or in case of text kind of processing, we were calling something known as edit distance, right? So like that, here we have this notion of measuring the effectiveness of the straight line based which you fit based on the absolute error, so root mean square error, or absolute error, or relative absolute error, or root relative squared error. So it's up to you what to choose, but most commonly what people give is root mean square error, which is the most common indicator of how effective what you have discovered is for modeling the data set. This is a very powerful statistical indicator. But usually what happens is, if you look at several of these variables, it is not that all the variables are equally correlated with the output. When you get the equation, in some cases you find that the correlation is positive, means that if the value of that variable, independent variable, let's say sugar, diabetes was your case, and in this case weight, is most likely a positive correlation, in the sense the more the weight is, as you increase the weight, the chances of diabetes increases. In some cases it could be negative, in the sense that if something like your I don't know, exercise, if you're doing more exercise, it's possible that your diabetes is coming down. So when you get an equation, you typically will have a combination of some positive, some negative coefficients which indicate the relative correlation between that particular variable and the output variable. So you have to be aware of this. Whilst linear regression is usually going to give you one slope, it could be either a positive slope or a negative slope, but in terms of individual dimension, it could be a negative or a positive correlation. So you clearly saw that in this case we are talking about fitting a straight line which is useful for modeling the data set. You see that for a data set you can have any number of linear classifiers, a multiple number of linear classifiers. You see the diagram? Is it clear? There are multiple linear classifiers which can be used to describe the data. And that is usually a problem when it comes to modeling data using linear regression. So what machine learning community has come across is, hello? Okay. So the key difference between, when we work with one linear classifier and what the possibility is that here we talk about different number of linear classifiers for the same data set, right? And that is usually a challenge in the sense which will say, okay, here is my straight line classifier. Is this better than yours or something like that? So what machine learning scientists have done is they have overcome this problem by introducing a very interesting notion called margin. So margin is basically the notion of a linear classifier supported by a width that the boundary could be increased before hitting a data point. So you see this here in this case, we are finding that the maximum margin linear classifier is the linear classifier with the maximum margin. Means what is that band of classifiers which can separate neatly the samples, and this is where we call it the maximum margin linear classifier. But then we have a new concept which is saying that if you take the band of separation, which is your margin, plus the data points which are on the margin, which are on the boundary of this margin, those we call them support vectors. So what we end up with a far more granular separator or a classifier which is capable of separating all the data points with a robust description, which is I'll have one unique margin plus set of points on the boundary. These are called support vectors. That is what is known as SVM, support vector machine. So for a classifier in SVM, we only talk of one support vector machine. You cannot talk of multiple linear classifiers because it generalizes the notion of linear classifier to include a notion of what is the maximum margin to which all the classifiers will fall into, plus include what are the boundary data points. So SVM is a very interesting generalization and a very interesting find in machine learning parlance. It is very stable with changes in data. and it is very commonly used in machine learning for very fast implementations of classifiers in several interesting applications. So with this, I would like to stop here, and we'll tomorrow see examples of linear